Good evening, everyone. Welcome to our sixth weekly discussion session for the Physics of Nanoscale Devices NPTEL course. My name is Jyotishwaran. I'm a PhD student from the Department of Electronics and Communication Engineering, IIT Roorkee. Moving on to the topics we shall be covering today. So, this week we shall be looking at the modes. Essentially, we shall be working with the conductivity of ballistic channels. So to start off, we shall look at the modes in a ballistic channel. So this is a continuation from last week's discussion. We shall look at how to explicitly calculate the number of modes in a channel in certain specific cases. And after that, we shall look at the properties of the ballistic conductance of a channel in certain specific conditions, especially that of low bias and combined with T equal to 0. This is what we shall refer to as the low temperature case. So whatever results we obtain here is true for sufficiently low temperatures also. Like essentially this is true for any temperature in the neighborhood of 0. Like up to a few kelvins, these rules that we are going to obtain are applicable. And then we shall look at the evaluation of the conductance at higher temperatures under the same low bias conditions, and then we shall conclude our discussion with some properties of the Fermi integrals, and that will be all for this week's session. So, starting with our first topic. So, as seen last week, the current through a ballistic channel is given by this integral. So, we have been looking at this for the last 2 weeks actually. And what we concluded is that this quantity here, covered by the overbrace, is the number of modes in the channel. And this kind of gives us the probability of finding an electron at that particular energy. So that will kind of give us the current flowing through a channel. And we also looked at the specific case for a 2D channel where the number of modes was given in terms of the average velocity along the positive x direction. So here we have to understand that if we have a 2D channel, so this is our convention here. So if we have a 2D channel, so this axis we are going to call the y-axis, and this axis we are going to call the x-axis, and the current conduction is along the x direction. So this is where the current I is flowing. Let me just use a different color just to distinguish that. So the current is flowing in this direction. So since we are concerned with essentially what I mean is my junction 1 will be present. Yeah. So junction 1 is going to be present over here, contact 1 and not junction. Contact 1 is going to be present here and contact 2 is going to be present on this side. So the current is flowing from 1 to 2. We can assume these to be the source and drain. Although we are not looking at the transistor-like structures yet, we are still in the domain of the two-terminal devices where we have two bulk contacts and a channel which is mesoscopic. So this is the explicit number of modes given in terms of the density of states and the average velocity in the positive x direction. We know that this is m star, the effective mass of the electron, by pi h bar squared. So this we know. And we also know that this quantity is equal to twice the ratio of twice the value of the ratio between the channel width and the de Broglie wavelength. Essentially, what I mean is m to d is also equal to w divided by lambda of e by 2. So m, to be precise, this is lambda dB, essentially the de Broglie wavelength. So this is md of e. Yeah, I should have been clear with that. So this derivation was also done last week. So now we are going to use all of these results to make some explicit mode calculations. So this quantity, the Debye wavelength, is what I shall refer to as lambda dB of E. Okay, so essentially what we mean is it's the number of half wavelengths we can fit along the width of the channel. Alright, so moving on to the first problem. We have to calculate the number of modes in a 2D ballistic channel of width 10 nanometer at an energy of 0.1 electron volts above the conduction band. We have been told to assume that we are given that we can assume that the effective mass of the electron is 1.1 times the rest mass, the actual mass of an electron. So how shall we go about calculating this? So first we have been told that the energy E, let me use this, yes. So the energy E is given to be EC plus 0.1 volts. But however, since the energy is scalable, what we can do right here is we can assume EC is the zero level of our energy. Sorry, this is not volts, this is electron volts. Okay, so because of that, I can simply say E is equal to 0.1 electron volts. Now that that is known, we have to calculate the number of modes in this channel. So how do we go about it? We can do the following. So we have like two choices with us right now. So one, we can actually look at the modes expression over here and obtain the velocity and then multiply it by the density of states, or we can use the final result here where all we have to do is calculate the Debye wavelength. So, sorry. So, let us first calculate the Debye wavelength at 0.1. So, for that we will be of course assuming that the energy is p squared by 2n, where p is the momentum, is like it's the magnitude of the momentum. We are not worried about the direction here. So from this we will get, of course this is m star, this is not m. So from this we can say that p is equal to square root of 2 m star into E. No need to use the braces. Yeah, 2m star into E, and from that we can say lambda dB of E is going to be h by p. So since this is the definition of the Debye wavelength, all we have to do is this is equal to h divided by square root of 2 m star into 0.1. So taking the appropriate values, so just 1 second. Yes, so yeah. So for this particular problem, so this is how we calculate the number of modes, the Debye wavelength. So we can in fact go directly to the final expression and okay, so yes, so this is the Debye wavelength. Now we know that the number of yes, so whoever is attending the meeting, please kindly mute your mic because my voice is feeding back into, like it's feeding back to me. Yeah, thank you. So, yes. Wait, here it is. So, now we know the number of modes is equal to W divided by lambda dB. by 2, like it's 2 into W by lambda dB. So let me just insert a new slide here. Yeah. So from that we know the number of modes at this energy M of E is equal to 2 into W divided by H divided by square root of 2 M star into E, and this will be 2 into the width into square root of 2 M star into E, divided by H. So these values will be 2 into the width in this problem is given by 10 nanometers. So 10 into 10 to the power minus 9. I'm going to write all the units in all the quantities in standard units so that the calculation will be easier. 2 into the again for reference, the effective mass of the electron is 1.1 times the actual mass, the rest mass of the electron. So this is 9.1 into 10 to the power minus 31 into 0.1 into 1.6 into 10 to the power. Let me just make this slightly smaller, or better yet, I'll make the braces bigger. So yeah, multiplied by 1.6 into 10 to the power minus 19 into, of course, the 0.1 electron volts. So it is the square root of this entire quantity, the whole divided by 6.634. I'm just going to take it as, sorry, not 634, 6.62. So I'll just take it as 6.6 into 10 to the power minus 34. So even without doing the explicit numerical calculations, we can simply look at the powers of 10 over here. So essentially what we will get is 10 to the power minus 9 over here, and this is 10 to the power minus 50, the whole square root. So this will be 20 to the, sorry, I wrote it as square, I'm very sorry. It's the square root here. So this should be power half. So 10 to the power 50 will be 10 to the power 25. So 10 to the power minus 9 into 10 to the power minus 25 is 10 to the power minus 34. So the powers of 10 will cancel each other out. So we have 20 into 2 into 1.1 into 9.1 into 1.6. So that is why I kind of chose these particular values of energies and channel width, because the exponents will cancel out and we'll be able to clearly see where the number of modes is coming from. So 0.1 divided by 6.6. So let me quickly just calculate this quantity. So this will come out to be, oh, of course, yes, there is a square root here, not to forget. So this will be yes. So this quantity will come out to be 5.42. However, we know that the number of modes, again, this was discussed last week, is to be taken as the nearest integer. So therefore, the number of modes at this energy level is equal to 5. This implies there are 5 modes available for electrons to move from contact 1 to contact 2 in this 2D channel at this energy. So number of modes is equal to 5 at this energy, and we can see that from this expression the number of modes kind of scales as square root of E. So I could have also asked the question that what would happen at twice this energy. So we know that it will become square root of 2 times this. So that will come out to be approximately 7 modes. So for 2D channels, again, this has been discussed in week 3 actually. We know m is proportional to e to the power half for a 2D channel. So please remember the things from the previous week's subject matters, because your final exams will actually have questions of this form. It won't just be like calculate the number of modes at a given energy. It will be like if the number of modes at a given energy is some value, what will be the number of modes at say a different energy value. So you'll have to know these mode dependencies and based on that perform the appropriate calculations, because the only variable quantity here are essentially the width and the energy. If we fix the channel width, then the only thing the number of modes depends on is the energy. So just remember this, like this is just an aside. I thought it will be worthwhile mentioning it here. So this is problem 1. So now we shall look at another way to go about calculating the modes in a 2D channel. In fact, this can be used for even a 3D channel, but more specifically, we shall be we shall be concerned only with a 2D channel here. So at very low temperatures, that is T equal to 0, the number of modes in a channel becomes strongly dependent on the charge carrier density in the channel. In general, also this is true, but at low temperatures the dependence becomes explicit. So like it is going to directly depend on the number of charge carriers. So how do we find out the charge carrier density? So this derivation has been done in the class, but just for the sake of completeness, I will just say where we get this from. So essentially at t equal to 0, the total number of states that is occupied will be up to kf. So the total area in the k space, essentially, if I'm drawing this axis over here, kx and ky for a 2D system, then at the Fermi level, at 0 temperature, only energy levels up to the Fermi level will be occupied. Yeah, this is supposed to be a circle, so please understand that. So this will be kf. So only these states will be filled. Everything outside of this will be empty. Okay, so the interior of this will be, let me see if I can just, yeah, yes. So this entire region is going to be filled and everything outside of this is going to be empty. So the total number of occupied states is pi kf squared, because it's a circle, and we know that the k values have a spacing. Like if my system has like, yeah, let me just go back here. So in this discussion we shall assume that the channel length over here, yeah, so let me just say this quantity here, let me call this L, and this quantity here, the width is W. So we know that, again, this we are going all the way back to week 2. We know that delta kx is going to be pi by L and delta ky is going to be pi by W. Therefore, the area occupied by a single electron in this k space is going to be pi squared divided by a. And for each such k point, there are going to be 2 electrons. So from this, we will say that the total number of electrons like in the system is going to be, so this is the number of occupied states. Let me not put too many arrows. So this is number of occupied states, or rather this is the area of occupied states. This is not the number. The number we will get by dividing it. So this is the area of the occupied states. The total number of electrons n is therefore going to be this divided by, so it is going to be pi into kf squared divided by pi squared times L into W, which is the delta K values, because a unit area is going to be like delta Kx and delta Ky. It's going to be a square, not a square, a rectangle in general of this form, a single unit area of that kind. And for each such state, there will be 2 electrons. So I'm going to multiply this by 2. Yeah. So this will imply n is equal to L into W into kf squared by pi, sorry, 2 into. And of course I can divide, this is the area of my channel, so I can divide n by area. Therefore ns is equal to, oh no, I'm sorry, the 2 will not be in the numerator. So each of this corresponds to 2 states. So the 2 will be in the denominator. Apologies. Yeah. So yes. So from this we will get the expression over here. Kf squared upon 2 pi. So this is the relation at t equal to 0. So, but I mean, since the value of Kf does not change with temperature, we can say that this is true for all temperatures also, but we have derived it by considering the t equal to 0 case. Okay. So, and added to this, the number of modes will only be calculated at the Fermi level for the low temperature case. Now, why is this so? Because at low temperatures, the highest occupied energy level is the Fermi level. And we have discussed, like from our initial weeks, that typically, so if I have a band in my system, the band edge or the highest occupied energy levels are going to be the Fermi level. So if any conduction is going to happen, it is only going to happen at the band edges. This was discussed in I suppose week 2 of our discussion sessions and the corresponding lectures in the course. Because of that, conduction will only be contributed by electrons which are around the Fermi level. So now using this, let us do some more problems. So now we have to find the volume relation between the volume charge density given by small n and the Fermi energy EF in a 3D channel. So essentially whatever we did here, that is why I briefly did this calculation here, because one of our problems is going to be this. So yes, so how do we do this? So at t equal to 0 Kelvin, we know that all levels up to EF are occupied. Which implies the total volume in the phase space is going to be 4 by 3 pi into Kf cube. So this is the total volume in the, I shouldn't say phase space, it is the K space. It's the reciprocal space. So this is the, I shouldn't use the term V because V I shall be using later on. So I am going to just refer to this as volume in K space. Alright. So now how do we go about calculating the, wait, did I make a mistake here? Yes, indeed I did. So, no, I did. No. There are no mistakes here. Yes. So, Now we also know that the volume, or oh yes, I did. So delta kx is not pi by l, it's actually 2 pi by l and 2 pi by w. Yes. Yeah. Which is why there will be a 2 over here and this will be 4 pi squared, and so finally all of them will cancel out and I will get this. Yep. Apologies for that mistake. It has been corrected. Yes. So a single, now volume of a single state is going to be, so this is volume in K space, volume for, so volume of a single state is 2 pi the whole cube divided by, of course there is going to be a length, width and depth for this channel. So the whole thing I'm just going to multiply and write it as the volume. So it's going to be this quantity V. So now total number of electrons in this channel N, oh no, capital N. So the total number of electrons, capital N, again same as before, it is going to be 4 pi by 3. So 2 into 4 pi by 3. Oh, oh come on. Yes. Yeah. So 4 pi by 3 into kf whole cube divided by 2 pi whole cube upon v. So from this we shall get, this implies n is equal to 8 pi by 3 into v into kf cube divided by 2 pi the whole cube. So this is going to be 8 pi cube. So the 8 and 8 is going to cancel out. And I can take n by v over here. Therefore, small n, the charge carrier density is equal to kf cube divided by 3 pi squared. So this is the relation between the, this is the relation between kf and n. But we have been asked to find the relation between the Fermi energy and n. So how do we do that? It's actually pretty straightforward from there. So we know that EF is equal to h bar squared k squared kf squared by 2m star. So we know this to be true. Therefore, EF, or rather kf, is equal to 2m star EF divided by h bar squared whole bar half. So where kf cube was present in the previous equation, we'll just substitute this. So n is equal to, it was kf cube by 3 pi squared, right? Yeah. So yeah, so this is going to be 1 by 3 pi squared into 2m star EF divided by squared whole power 3 by 2. This also kind of, yeah, so this is the relation between N and DF. This, like for people who have been like following the derivations that we have been doing, this kind of makes sense because we know that the density of states, D of E, is proportional to square root of E for a 3D channel. So, and we know that the number of electrons is integral d of e times f of e. So we essentially have something that is proportional to square root of e. When we integrate that, we will expect to get a factor of e to the power 3 by 2, which is what we have obtained here. So the number of electrons present, or rather per unit volume, is going to be equal to the Fermi energy whole power 3 by 2, of course multiplied by constants. Similarly, if we go back to this case, we will see that it is directly proportional to the energy. That is because, of course, dE is a constant, which implies when I'm integrating it with respect to energy, I will get an e to the power 1 term. So again, these quantities, these equations and expressions that we are writing here, they are not as something totally strange. These are just a logical continuation of what we have been doing thus far in this course. So now we are coming back to more numericals. So first, we shall calculate the number of modes present in a 2D channel at t equal to 0 Kelvin if the surface charge density is given to be 10 to the power 10 per centimeter square and the channel width is 15 nanometers. The second part is what would be the value of the resistance, not if, of this channel B. So yeah, these are the two things that we'd like to find. So here essentially what I mean by this question is we want kind of a relation between the resistance R and M of E. This is what we want to understand for now. Okay, so let us calculate the first part. First, we have been given that Ns is equal to 10 to the power 10 per square centimeter. So this implies Kf is going to be square root of 2 pi Ns. Now what we are going to do is, instead of evaluating these one by one, we shall directly try to arrive at the final answer in terms of these quantities. That will be helpful for you to solve certain assignment and other questions in the future. So this is Kf. Now how is Kf related to the de Broglie wavelength? So we know K is equal to 2 pi by lambda. So this is the relation between the wave number and the wavelength. So like omega is 2 pi nu, the angular frequency is 2 pi into the linear frequency or the frequency, and the wave number is 2 pi divided by the wavelength. And what we need is, so this is going to be lambda dB, because again, remember this last statement here, we are only going to be calculating the number of modes at the Fermi level, which is why the energy we are concerned with is the Fermi level. Since the energy we are concerned with is only the Fermi level, what we want to find out is M at EF. This is the quantity that we want. So to calculate M at EF, what do we have to do? It is 2 into the width of the channel divided by lambda dB, the de Broglie wavelength evaluated at EF. Now, I have given what KF is. So, and I have given the relation between K and lambda de Broglie. So, all I have to do is substitute that over here. So, this is going to be 2 into the width of the channel divided by, so 2 pi by KF. So, this is going to be width of the channel into Kf divided by pi. So this is the explicit expression for the number of modes at the Fermi level at t equal to 0 Kelvin, not for any arbitrary, oh no, wait, I'm sorry. Let me hold off on that statement. I will come back to it in a second. So this is further equal to into square root of 2 pi ns divided by pi we can also like just to finish this whole thing, this is going to be 2 ns divided by pi whole power half. So this is the quantity. Yes. Yeah. So now we have yeah, apologies for the interruption. I had a surprise visitor. Uh, so yes. So now we know that the number of modes at the Fermi energy is going to be W into 2 times ns divided by pi whole power half. Now we know ns is, we have been given that ns is 10 into 10 to the power 10 per squared centimeter. So now this is going to be like if we are writing it in terms of like, since I told I'm going to write everything in meter squared, so I mean in standard units, this is going to be 10 to the power 40 per square meter. So from that, yes, this is correct. Yeah, that is correct. So now the width is going to be 15 nanometers, right? Yes, it's going to be 15 nanometers. So 15 into 10 to the power minus 9 into 2 by pi into 10 to the power 14 whole power half. So now this will come out to be so this is going to be like square root of 2 by pi is approximately 0.8. So this is going to be 15 into 0.8 into 10 to the power minus 9. There's a 10 to the power 4 here, so this is going to be a 10 to the power 7. Yeah. So this will give us a value of, so this is 15 into 8 by 10, so that's 120 by 10, which is 12 into 10 to the power minus 2. So as you can see, in this case, the number of modes comes out to be 0.12, which implies m of EF is equal to 0. So the reason, again, these values were chosen is to kind of give us an idea of the charge density we are expected to find in devices. Now, for people who have been studying semiconductor devices, you'll know that an intrinsic carrier density of 10 to the power 10 centimeter squared is actually pretty less. And such materials will tend to show insulator-like behavior. And that has been established, or rather re-established over here. So if I assume that the intrinsic carrier concentration is only 10 to the power 10, then by calculating the number of modes, we have found out that there are no modes available for conduction. Okay, so this implies no modes. If there are no modes for conduction, that implies there is no conduction that is going to occur in this channel. Now I hope the second part of this question makes more sense. What would the value of the resistance of this channel be? Since this is not a conducting channel, the resistance, this is an insulator. So theoretically, like in the theoretical region, like in a theoretical sense, we can say that the resistance of such a channel is infinite. Because it doesn't matter what the temperature is, it doesn't matter what the applied voltage is, because I have no modes for conduction because of the available number of electrons. So this problem was to show that the charge carrier density, of course, like I mean, it's only establishing a very basic concept that we have known all along, that in order for current conduction to take place, we need enough electrons. Now, how many electrons is enough? Well, now we know 10 to the power 10 electrons per centimeter squared is not enough. So, I mean, now that we have arrived at this point, let us say I am going to just redo this problem with a slight change. So, I will assume Ns is equal to 10 to the power 12 per centimeter squared. So, in this case, this is going to be equal to 10 to the power 16 electrons per meter squared. That implies now the number of modes M at EF is just going to be 2 into 15. Oh no, why 2 into 15? It's just going to be 15. Yes. Again, like we have calculated all these quantities, so only this is going to be replaced by 10 to the power 16. So other than that, everything is going to be the same. So this is going to give me, since it's 10 to the power 16, it is going to be a power of 8. So the quantity is just 15 into 0.8 into 10 to the power minus 9 into 10 to the power 8. So I'm still going to get it 10 to the power minus 1. However, in this case, this quantity will come out to be 1.2. So now I can say that M of EF is 1, and from this point onwards, conduction is possible in the channel. Now, how to calculate the explicit resistance for this channel, we have not seen that yet. So this implies a minimum of 10 to the power 12 electrons per square centimeter is required. I mean, the thing is not going to be exactly 10 to the power 12, like approximately. Okay, it can be slightly less than this also, because I don't need it to be 1.2, I need it to be exactly 1, but you know, it's going to be in the neighborhood of 10 to the power 12 electrons per square centimeter. So is required for conduction to take place such a channel. Now, so such calculations will inform us what kind of materials we need to select to fabricate channels of a given dimension. So if I want a channel in the nanometer region, I cannot just use, again, I will have to choose a material which has a charge carrier density that is in this region. So if I'm just using an intrinsic semiconductor, to increase the charge carrier concentration, I will either have to dope it or use other methods where the effective number of electrons present for conduction is suitably increased. So these values that we obtain here inform us on those choices. So these are not just theoretical calculations, they also have a direct impact on the selection of materials for the device, or we can go the other way around also. Given the properties of a material, we can find the width for which I can have at least one channel, one mode present. So that could have also been done. So in that case, what we would have had is like 15, like conversely, instead of changing Ns, had I wanted to change W, you can see that increasing W by a factor of 10. Like from 15 nanometers to 150 nanometers, we'll find that for such a material, there will be one mode present. So both of these can be inferred by this relatively straightforward calculation. So that is what I wanted to cover in this problem. Now, yeah, moving on. The second topic that we shall be looking at is the conductivity of a ballistic channel in the low bias condition. What do we mean by low bias condition? We mean that this voltage is very small. So again, I'm not going to go through this entire derivation. However, we shall be doing a different derivation at the end of today's session. that is going to take the bulk of today's session. So here, the current is given by this integral. So essentially what happens is this F1 minus F2 for very small biases can be approximated by the derivative of the Fermi distribution function. And this is the applied bias, which implies I upon V, like current divided by the voltage. This is going to be the conductance is going to be 2q squared upon h integral. Now we know that this quantity here is, I mean, this of course is the mode. So this whole quantity, like completely multiplied, I'm just going to write this, or rather, to be more precise, let me take the 2q squared upon h inside times g of e. Oh no, I shouldn't write this as g of e. Yes, I will write this as m of e dou f upon dou ef dE. So this quantity right here, this is what we call the conductance at this energy E. And the factor, the constant factor that we are multiplying here, this is known as the quantum of conductance. What do we mean by quantum of conductance? What we mean is this is the value of the conductance if only one channel is present in the, one mode is present in the channel. So this is the conductance per mode. So that is the quantum of conductance, and we know 1 over 2q squared upon h is 12.8 kilo ohms. So this again tells us, am I writing this correctly? Yes, this is correct. So just 1 second. Let me just double check this once to make sure I'm not making any mistakes. Yeah, it's 12.9. Yes. So kilo ohm. So this is the, like, I mean, when we construct channels, when we construct a ballistic channel, whatever the number of modes is, it is essentially going to be multiplied by this quantity here. So this represents what range our resistance values are going to be. So they will be in the kilo ohm region, and like depending on the number of channels, it will be multiplied by this factor, and this will kind of tell us how much power is going to be dissipated in devices we fabricate which work on these principles. So again, this simple looking quantity here informs us about the physical functioning of the device. So this expression here at low temperatures, this quantity dou f of e by dou ef, it takes the form of the Dirac delta function. So delta E minus ef is the Dirac delta function. Yeah, this is the Fermi Dirac distribution, and this is the Dirac delta function, both of which are named after, like, at least partly named after Paul Dirac, one of the founding fathers of quantum mechanics. So, and to reinforce now, the conductivity at low bias and low temperatures depends only on the number of modes at the Fermi level. So what we calculated, what I mentioned here for the low temperature case is now augmented further by the statement. For low biases, it is explicitly only dependent on the number of modes at the Fermi level. None of the other modes will contribute to the conduction when I'm having very low bias. And this kind of makes sense because when the bias is very low, it means the Fermi levels at contact 1 and contact 2 are almost the same. Since they are almost the same, only electrons very close to that Fermi energy are going to participate in conduction. Okay, so moving on. Ah, okay, yes. So now first we have to prove that this quantity is 1 for all temperatures. I have told that this is the Dirac delta function. Now we cannot substitute that here, and even if we were to substitute that over here, yeah, if we substitute that over here, we will directly get the answer. But that is true only for t equal to 0. So for t not equal to 0, what we have to do is we will have to like explicitly calculate the derivative. So let us do that first. And remember here the derivative is taken with respect to the energy. So yeah, again, like one could have directly said, okay, now this is f of 0 minus, or rather f of infinity minus f of 0, yes. Not f of 0 minus f of infinity. One can directly just perform this integral and say this is f of 0 minus f of infinity. We know that f of infinity is 0, and we will try to find out what f of 0 is. But the point is f of 0 in general is, I mean, it will depend on the Fermi energy. So this will not give us a value of 1. However, I am saying that this quantity will always integrate to 1 at any temperature. So directly performing the integral will also not be helpful to us. So what we are going to do is first we are going to calculate the partial derivative of the Fermi distribution function with respect to the energy. So this is by dou E of 1 by minus e to the power E minus EF upon kBt. So now this quantity will be, essentially it's, we just have to like use the chain rule. So this is going to be minus 1 divided by 1 minus e to the power E minus EF by kBt whole squared into, we'll have to take the derivative of this quantity here. So that is going to be minus 1 over kBt e to the power E minus EF by kBt. Like when we take the derivative of the denominator, it's going to be the derivative of, like, 1 will differentiate to 0, and this quantity here, the derivative will be the exponential function, and then we will take the derivative of the exponent itself, and that will come out to be this. So our final quantity is, yeah, so this is going to be 1 divided by 1 minus, sorry, not 1 divided by, it's going to be 1 by kBt, apologies, kBt into e to the power E minus EF divided by 1 minus e to the power E minus EF upon kBt whole square. So now this is going to be, like, if I assume E minus, not E minus, if I assume e to the power e minus ef kVt to be some quantity, let me call it y, then this is 1 over kBt times y divided by 1 minus y squared, sorry, 1 minus y the whole squared, oh, apologies, yeah, 1 minus y the whole square. Now we can plug this back into the integral. Since I've made this substitution, I can say that dy is equal to e to the power, or rather it is going to be, so if this is y, then I can just do dy by de, and so that is going to be 1 over kBt into dy by de will be this, yeah, de divided by y. Is this correct? I'm sorry, just 1 second. So dy by d will be this. Oh no, I made a mistake. So it is going to be e to the power e minus ef divided by kBt into 1 by kBt de, which is equal to y by kBt into de. So this is kind of why I did this substitution. So now the integral de will become from 0 to infinity, will equivalently be written as 1 by 1 minus y whole squared dy. Now the limits here, so this is where I shall be making a small approximation. So at e equal to 0, this quantity is e minus ef by kBt. For most like macroscopic systems, like if I even have say 10 electrons in my system, then the Fermi level is going to be like, oh, I'm sorry. Here, yes, for all temperatures, right? Yeah, correct. So even if my system has only a finite number of electrons, the Fermi energy is going to increase linearly with the number of electrons. Not linearly, it is going to increase with the number of electrons. So the more electrons we have, the more the higher EF will be, which implies the smaller this quantity will be. So this integral is still approximately going to be, yeah, I know I was saying that we are going to prove this exactly, but I will tell you why this is exact in a second. So this is approximately equal to 0 to 1 from this. Now this integral we know can be evaluated to be minus 1. Sorry, not 0 to infinity. So this integral will take the value minus 1. And yeah, I made a mistake here. So this should not have been equal to 1. This should be equal to minus 1. Just 1 second. No, don't draw. For God's sakes. Yeah. Yes, now this is correct. So this integral will be evaluated to be minus 1. Now why is this true? The answer is actually not that hard to see, because again, as I mentioned before, for large enough systems, we can always, it is a fair assumption to make that the lowest energy state is going to be occupied. Like the lowest possible energy value an electron is going to have, even if we look realistically in a solid, excitations are only going to occur between the highest occupied energy level and the lowest unoccupied energy level. We are very rarely going to find cases where the energies, like the electrons are going to transition from, I'm sorry, electrons are going to make like excitations from any bands lower than that. So because of that fact, since we are typically talking about materials that are, that have multiple electrons occupying multiple bands, and this particular, the lower limit of this integral can very well be set to 0. Okay, so that is the first part done. Now the form of dou F by dou E at low temperature. So this is the second part of the question. So how do we do this? We will do this by the following method. So we essentially want to evaluate this quantity dou F upon dou E. We want to do this at essentially t equal to 0. So we can look at the function form of it. So for that, let us first, yes, draw this. So at t equal to 0, the Fermi function is going to look like this. So it is going to be 1 until the Fermi level. So this is F and the x-axis is the energy. So it is going to be 1 up to the Fermi level and then it's going to drop to 0. So this is how this function is going to look. So how do we represent this in a functional form? Like, of course, we can simply say, okay, I am taking the derivative of this function. But rather than doing that, I want to write, like the reason I am doing this particular exercise is, I want to write this as an explicit function. So the function that I am going to use is the theta function. So what is theta of x? This is called the step function. So this is going to be 0 for all x less than 0 and 1 for all x greater than or equal to 0. So this is the unit step function. And now you can see that the Fermi distribution function at 0 Kelvin very closely resembles such a function. So this is the unit step function. People who have studied some signal processing or any other form of differential equations and say Laplace transforms or things like that will be familiar with the unit step function. So now I can write f of e at 0 Kelvin as, so I can also write this as x minus x naught, in which case this, instead of being centered around 0, it is going to be centered around some point x naught, and theta of minus x is going to be the reverse. It will be 1 for negative x and 0 for positive x. So f of e can essentially be written as this. It can be written as, it can be written as theta of minus e minus ef, or rather, am I writing this correctly? No, it is minus of e minus ef, yes. So minus of e minus ef. So what will happen to this? So minus of e minus ef means when e minus ef is negative, this function is going to be 1, and when e minus ef is positive, it is going to be 0. So up until here, it is fine. But after this, the function again has to become 0, because negative energies, I do not consider them. The lowest energy always starts from 0. So to take care of that, what I will do is I will take another theta function of this form and just subtract it. So that is going to be minus another theta of minus e. So this is the form of the Fermi distribution function at t equal to 0. Okay, so now what we can see is, or rather, you know what, yeah, this is problematic. So I'm just going to write it like this. Because the truth is, I don't actually know where my zero energy is. Because when I have very large number of electrons, for all intents and purposes, the zero with respect to EF is going to be very far off. So I'm not going to worry about the second theta function. So yeah, this is enough for me. So when I do dou F by dou E, what we will be doing is we'll be taking the derivative of the unit step function. Now the property of the unit step function is when we take the derivative of the unit step function, we will end up with the delta function. So d by dx of, or rather let me just maintain color consistency over here. So d by dx of theta of x is going to be delta of x, the direct delta function. So we are going to do the same thing here, but instead of theta of x, we are going to have theta of minus x. Therefore, the derivative is going to be, it is going to be minus delta of E minus EF. Okay. Apologies. Yeah, E minus EF. So this is the explicit form of the derivative of the theta function. So this is what, of the theta function, which happens to be a Fermi distribution function. So this is what was mentioned here. In the class, you might have had a different derivation where you considered the curve and then took the limit where t tended to 0. But here I'm just writing the explicit function form and just simply differentiating it to show that even if we follow this method, we'll arrive at the same result. Now, since this is true, and we know dou F by dou E is equal to minus dou F by dou EF, this will be equal to, this implies dou F by dou EF, which is what we have in our current integral, will just be the Dirac delta function E minus EF. And the property of the Dirac delta function, from here, I can simply say that if this becomes the Dirac delta function, my number of modes is just going to be m of EF, and the conductivity is just going to be 2q squared by h into MEF. So that is the ballistic conductance. And if my channel were to be large, like if I'm tending to the diffusive limit, there will of course be a factor of T of E multiplied to it. And as we have discussed before, again, T of E is always going to be a fraction. So the number of modes will be reduced by as the channel length increases. So the transmission coefficient is a fraction. Just 1 second. So yeah, the transmission coefficient is a fraction. Because of that, the conductivity is always going to be less in the diffusive limit. So since T of E is a fraction, now I'm not going to write this in the slide for obvious reasons. But for those who are listening to the video, now you know. Because this integral in the diffusive limit, there is going to be a factor of T of E, and T of E is always less than 1. Because of that, the number of modes available in the ballistic limit is always going to, in the diffusive limit is always going to be less than the number of modes that is present in the ballistic limit, which implies the conductivity is always going to be less in the case of the diffusive limit when compared to the ballistic limit. Okay. So now, yeah, the incorrectly numbered problem 4. This is actually the 5th problem. This shall be the final problem we shall consider for today's session. So, and this is going to be a derivation, because if this calculation is not being done, then it is not possible to do any calculations, and I will just be repeating what was present in the slides. I'll just be displaying what was present in the slides. This is also technically a repetition, but we will be going through this step by step for the sake of revision. So derive the expression for the current in a 2D channel for low bias and non-zero temperatures. So since the temperatures are non-zero, I can no longer use this Dirac delta approximation. So now we have to find out what the expression is. Of course, if you have followed the lectures, you'll know that the Fermi integrals will start appearing in it. And so we shall see how they enter the picture. Now, of course, for small biases, we know this is true. The current is equal to 2q squared upon h integral. Now, so this is a 2D channel, right? So what I'm going to do is, since it is a 2D channel, I'm going to go ahead and use this expression over here. Okay, I'm going to use this expression for the modes because we have established this to be true for all energies in a 2D channel. So the modes is now going to be just 2 into the width of the channel divided by the, or rather, oh no, not rather, no rathers. Yeah, so this is going to be, yes, divided by lambda de Broglie at E into dou F by dou EF dE, the whole multiplied by the voltage V. So this is going to be 0 to infinity. Now again, like technically speaking, I'm supposed to start this integration from the edge of the conduction band. I'm not going to bother with that because I'm setting my 0 at, so I'm essentially doing this EC is equal to 0. So my integration starts from the edge of the conduction band because those are the only electrons that are physically going to contribute for the charge conduction through the channel. So anything below that, these quantities, like many of these quantities, will become 0. So essentially dou F by dou EF will become 0 for those values. Only around this point will this even be non-zero. So I can perform the integral in that region only. Okay, so now this is going to be 2q squared upon h into 2 into w divided by, now this we are going to write the momentum. So this is going to be square root of 2 m star into E integral 0 to infinity times, now dou F by dou EF is e to the power E minus EF into minus 1 by kBT. Oops, the T should not be in the subscript. Divided by, oh no, the minus and minus will actually cancel each other out. So, yeah. One minus e to the power E minus EF by kBT, the whole squared. Is this correct? Yeah, this is correct. Apologies. Yeah. Into V. So this is the complete expression. Now, yeah. So now what we are going to do is we are going to consider oh no. Oh no, this is not, I mean, this is fine. Yes. So sorry, I got confused for a second. Yes. So Duplicate slide. Oh no, not duplicate. Insert a new slide. God. Yes. So now this is going to be, yes, I is equal to 2q squared upon h. So now what we can do is this. I should not have done this actually. Yeah, so let me not do the differentiation here. Yeah, that was the mistake I made. So what I'm going to do is, I'm just going to write this as the partial derivative itself. Yeah, that was the one small mistake that I made. It has been rectified. Okay, into V. So this quantity is over here. Yes. Now moving along. Oops. Sorry. Yeah, I minimized it. Now what I can do is, this quantity is a partial derivative with respect to the Fermi energy. This integral is with respect to the energy E. So these are two independent variables. So the order in which I perform these operations is immaterial. So that is exactly what I'm going to do. Instead of integrating the derivative, I'm going to differentiate the integral. So I'm just going to bring this quantity out here. Oh, not dou E. It's dou by dou EF. Dou EF times integral 0 to infinity 2 into W divided by square root of 2 m star E into, yes. So now I can directly write the Fermi function over here. Yes, now we are on the right track. 1 plus e to the power. Oh god, no wonder. Yes, I was making a grievous mistake through and through. So these are all pluses. So there is not going to be a -1 factor here. And there is going to be a -1 factor over here. Yes. I'm really sorry for this oversight. In the previous problem, I wrote the wrong form of the Fermi distribution function. Uh, Apologies for that. I've corrected it once again. Yes. E minus EF upon KBT. Yes. So D. So I'll first perform this entire integral, then I will take the derivative with respect to the Fermi energy. Now, furthermore, I can pull out all these constants outside. So that is going to be 2q squared upon h into 2w divided by square root of 2 m star. So all of these constants will come out. Dou EF integral 0 to infinity e to the power minus half divided by 1 plus exponential e minus EF by kBt. So now what we are going to do is we are going to make the following substitutions. We are going to say this quantity eta is equal to E by kBt. We are essentially normalizing the energy, or rather non-dimensionalizing the energy, and eta F is EF by kBt, which implies d eta is going to be dE by kBT. So I'll multiply and divide by a kBT here. So the kBT will also jump outside, you know, multiply and dividing all these things, it is going to be 2 root 2, or yeah, I'm going to do this, I'm going to write this as 2 q squared by h into w into, oh yes, the whole thing is still multiplied by the voltage, not to be forgotten. So dE into V. Okay, so yes, into 2 by m star whole power half. Now since I will multiply and divide by kBT here, a factor of kBT will also jump outside. Yes. Dou by dou EF, integral 0 to infinity, eta divided by 1 minus e to the power eta minus eta f. So this is eta to the power minus half. So now this is the dE into V. Okay. So now this quantity is what is called a Fermi integral. Okay, so this quantity right here is what is called the Fermi integral. I'm not including the derivative. Please note that. So this is the Fermi integral, and notation wise, the Fermi integral will be written by a script f. So it will be written as f. So this is minus half of eta f. Remember, the integral is done. Oh no, this is not dE. I'm sorry again. This is going to be d eta. Yes. So this is going to be d eta. So since I'm integrating with respect to d eta here, the eta dependence will vanish once the integral has been evaluated. The only variable here will be eta f. So the Fermi integral is always defined as a function of the Fermi energy. Okay, so this is how we write it. And the power of eta that appears in the numerator is the order of the Fermi integral. So the order of this Fermi integral is half. Okay. So now, like what does this, like, so this is the expression for the current through a ballistic channel, low temperature, low bias. Sorry, low bias, non-zero temperature, not low temperature. Okay. KBT into, yeah, another multiplication over here. So now this entire factor, what I'm going to do is, I'm just going to call this constant, what shall we call it? So let me call this constant some k naught, yes. I'll just call this some k naught, okay? Or rather I will call it k2d. So this is the constant k2d. Okay, so now the current expression I is equal to k2d into dou by dou EF integral, or rather now I don't even have to write the integral. I will just write this as dou by dou EF of the Fermi integral minus half of eta f. Okay, so this is the expression for the current. Now one would be tempted to say that the order of the Fermi integral that is appearing is minus half. But that is actually not true. So why is that? Because what will happen is when I'm taking the derivative, so the Fermi integral now, okay, so yeah, there is another, so this quantity is what we call the Fermi integral, but to be more precise, I should have done something more here. Yeah, I made a small, like a factor is missing. So this is proportional to the Fermi integral. This is not exactly the Fermi integral. So now I will just instead of writing the current expression, I will just define the essential properties of the Fermi integral. Yes, so the Fermi integral n of eta f, or rather let me say, let me not use n because n and eta might become confusing. So I will just call this Fermi k of eta f is given by 1 over gamma of k plus 1 integral 0 to infinity eta to the power k divided by 1 plus e to the power eta minus eta f d eta. So this is the integral. So 1 by gamma k, 1 by gamma k plus 1 is important here. Okay, so yes, this complete quantity is the formal definition of the Fermi integral. Yes, so this is the Fermi integral. Now the gamma function is the generalization of the factorial. Gamma of k is going to be integral 0 to infinity t to the power k minus 1 e to the power minus t dt. So this is the definition of the gamma function. So this kind of generalizes the factorial. For integers, gamma of k, not integers, for natural numbers or whole numbers, gamma of k is going to be k minus 1 factorial. So this is, I mean, yeah, 0 factorial is only defined as a formality, so I can just say that this is for natural numbers, this is what it is. For other values, the gamma function is defined as this integral over here. And the property of the gamma function is gamma of k plus 1 is k times gamma of k. And gamma of half, so this integral can be evaluated. So this is square root of pi, which implies gamma of minus half, which is actually 1 minus half, will be, I can essentially write gamma of half as 1 plus minus half. So it is going to be half into gamma of half. So this is going to be root of pi by 2. So gamma of minus half is supposed to appear in this Fermi integral over here. So yeah, so gamma of minus half is supposed to appear over here. So we will have a normalization factor of 2 by square root of pi also occurring in our thing. So the integral expression now can be written correctly as whatever this quantity was, I will insert 1 by root pi by 2 over here. So let me just, instead of defining k2d over here, let me just redo this so that there is no confusion. Okay, so yes. Oops. Yeah. So this is going to be, let me just, can I do that? Let me just rewrite this whole thing. This is going to be 2q squared into w, 2q squared by h into w into w into kbt into, so 2 by m per half. Now what I'm going to do, I will have a 2 by pi over here also. So I will just write this as, just to make this whole thing compact, I shall write this as 8 by m star pi whole per half multiplied by dou EF Fermi integral of minus half. So this is the expression for the current. Now this quantity I shall write as K2D. So this is equal to I into V, yes, which implies I by V. I should just write this as K2D into dou by dou EF, this quantity over here. However, this derivative, another property of the Fermi integral is, yeah, this is the final part. So when I take the derivative of the Fermi integral, dou by dou eta f, just 1 second. Yes. So when I do this, fj of eta f, when this derivative is evaluated, what will happen is we will move down by one order. So this will become fj minus 1 of eta f. Okay. So therefore, the integral that is appearing here, since I'm taking a derivative with respect to EF, which is nothing but 1 upon kbt dou by dou eta f, this entire k2d, like another kbt factor will like get in there, so I'm not going to worry about that. I'm not going to reevaluate that constant. All I can tell is the current is proportional to, or rather the current by voltage, the conductance is proportional to the Fermi integral of order minus half minus 1, which is minus 3 by 2. So this is the correct answer. So the order of the Fermi integral that occurs in this expression is minus 3 by 2. In this channel is minus 3 half. It is not minus half, it is minus 3 half. However, if we consider a 2D channel with a large bias, like not the small bias case, we will find that the current will depend on f of minus half. However, when the bias becomes smaller, the current, or rather the conductance, will depend on a different Fermi integral. So this is the final point I wanted to make. Different quantities, like similar integrals, can also be performed to evaluate the charge stored in the channel, the current, and the ratio between the two. All of these things will depend on the respective Fermi integrals. One has to pay attention to where the derivative of the Fermi function appears in our like where this quantity dou by dou EF appears in our current expression, whether it appears or not. If we are looking at the low bias case, whatever answer we have for the high bias case we can just reduce the order of the corresponding Fermi integral by 1, because wherever the derivative appears, the order of the Fermi integral comes down by 1. So this example, I hope, has covered all the necessary properties of the Fermi integrals, and also an illustration of how the current the expression is obtained for particular conditions in a ballistic channel. So with this, we come to the conclusion of today's session. I shall meet you all again same time next week. Thank you.